The RTL was successfully developed for this ASIC/FPGA system. After functional verification, we also synthesize the unit into a gate-level netlist. Then timing verification was performed to verify that the system on chip multi-core system meets timing requirements. Once the design meets timing goals, the netlist is given to the physical design, which places and routes the design, and then finally the chip is built and tested. The high-level system design process applied in this design was as follows. First, I identified the system requirements, followed by writing the preliminary specifications and parameters, thus developing a high level of algorithmic models in both C and C++ and also in VHDL. After that, I refined and tested the algorithms and determined the hardware and software partitioning at a system high level. Then I defined the interfaces, and the software specifications were written to develop the prototype of the software. The hardware-software co-simulation was also performed. The hardware specification was developed with behavioral models for the system. The partition was developed with reference to macros. Several macros were developed, and the preliminary specification was written for those specific macros. At the top level HDL, I successfully determined the configuration and generated the top level HDL design. In parallel, I completed and generated synthesis scripts, synthesized with reference to the library, provided scan insertion, ATPG fault simulation, and also perform the final timing and power analysis. Also in parallel, provided functional verification with a reference simulator, developed and ran multiple test configurations, and measured test coverage. For those sections of the design that are full custom, we have the choice between manual porting and automated porting. Under certain circumstances, automatic porting tools such as Gigantic, Dream can be effective. These tools operate at the polygon level, automatically mapping transistors and interconnect from one set of design rules to another, and shrinking the design as much as possible. For large macros such as multi-core embedded systems, where simulation speed in the system environment may be an issue, it can be useful to include cycle-based simulation and/or emulation models. In general, RTL that complies with the coding guidelines will work with cycle-based simulation and emulation. However, test benches and bus functional models, unless coded to the same RTL guidelines, are important and effective for large macros. The product files, in addition to the RTL in Verilog and VHDL, we must include the synthesis and installation scripts. We include the reference library so that we can synthesize the design and verify that the installation was completed successfully. In addition, providing the reference library, scripts, and verification environment allows us to create this true environment. Porting the hard macros. For hard IP that was completely synthesized, the porting strategy is quite straightforward. We just resynthesize, targeting the new technology library, and repeat the physical design and timing model generation. Verification files. The entire verification environment, including any bus functional models, bus monitors, or other models, and some set of verification test cases are included with this design. The integrator then develops a test suite to verify the functionality of the macros. So the bus functional models used to develop and verify the macro can be used by the integrator to create a test bench environment for the system on chip unit. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on call operands and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is addition, subtraction, increment, decrement, transfer, logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. A process statement, which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statements inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture, like other concurrent statements. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression and comparison of the value of each of the choices while the when clause statement corresponds to the matching choice, which will make the statement to be executed. Part of the ASIC system on chip SoC design methodology is the functional verification and the manufacturing test verification. Therefore, my objective is to illustrate the SoC verification paradigm from a conventional verification process and universal verification methodology, UVM. Split transactors. So the objective is to move as much of the UVM test bench code onto the accelerator or the emulator box in order to speed up simulation. This means splitting each transactor, that is the UVM driver or monitor, into two parts: a lightweight proxy or a wrapper that continues to run on the host, and a synthesizable part, which is the BFM or bus functional model, that runs on the box and wiggles the pins of the device under test, the DUT. So in order to accomplish this task, the code has to be structured into two separate domains: an untimed HVL domain that contains the UVM environment or verification environment, and which must not contain any delays or clocks; an HDL domain that instantiates the DUT, the device on the test, and the synthesizable parts of the transactors can be run entirely within the box. The synthesizable test harness contains code to generate the clock and the reset, and the code to instantiate the bus functional models, the BFM. So the pin level interface and the DUT. The untimed test bench instantiates the UVM environment. So it is important to note the untimed test bench is that the virtual interface within the top level configuration object is set to point to the BFM interface within the test harness, that is top underscore HDL underscore th.bus underscore BFM underscore 0. This is a full hierarchical reference to the interface instance of the bus underscore BFM underscore 0 within the top level module. So when the UVM driver and monitor proxies communicate with the code outside the class-based verification environment using local virtual interface variables, they will actually be communicating with the BFM in the synthesizable test harness. The UVM code generator interface template file contains settings to include various user-defined code fragments required to define the UVM driver, such as the proxer or wrapper for the full driver transactor, much of which is implemented on the HDL side in the synthesizable bus functional model, BFM. Now I will talk about the test plan creation in the universal verification model. The tests are applied to the DUT and fed to the signal generator to generate the input to the bus functional model, that is the BFM, in order to drive it to the DUT device under test. The input monitor collects the status from the BFM, the bus functional model, to the DUT, and the output monitor collects the response out of the DUT, as it is illustrated in the system block diagrams of this presentation. The input packet and the output packet response is fed to the scoreboard and checker, and compares the response from the DUT device under test and the reference model output. The build phase and physical connection of all components are done through the test generator, or the test generator, and of the packets to the BFM is the most time-consuming of the verification process. And the run phase collects the process from the device under test into the output protocol monitor and calls it in the scoreboard, as you can see from the block diagram, to run the test cases on the device under test. If the test case or the test cases are clean, then you can report the results and get an actual report. As spring continues on to perpetuity, to infinity, I find myself traveling throughout the beautiful city of Medellin metropolis. For large macros such as multi-core embedded systems, where simulation speed in the system environment may be an issue, it can be useful to include cycle-based simulation and/or emulation models. In this framework, I will present the topics of placement and routing within an ASIC design methodology. However, before we start this segment, we need to talk about physical design methodology in general. So many interdependencies exist among placement, clock and scan optimization, wiring, as well as hierarchical design planning. The general design flow is as follows. First, identify connections to be optimized after placement so that they will not influence placement at all. These include the scan and clock interconnection latches, 2. Generate constraints for placement on the basis of a timing analysis done using idealized clock arrival times at latches and estimates of wire load and RC delay before physical design. 3. Perform an initial placement to determine an improved basis for constraint generation and optionally to fix the placement of large objects. 4. Generate new constraints for placement on the basis of a timing analysis done using the wire load and RC delay values derived from the initial placement. Perform placement. 6. Optimize the clock trees and scan connections. Then make logic changes, including changes to circuit power levels, to fix timing problems. Then 8. Legalize placement. And then generate the new timing constraints for wiring on the basis of a timing analysis done using the actual clock tree and wire load and RC delay values derived from the final placement. And then finally perform routing. So placement is often run before the logic has been finalized to obtain an early indication of the timing and wireability. At this point, the feedback may be used to influence the logic changes. This may also be the time at which the locations of large objects are determined. The placement program may run more quickly by not considering such details as legality, and there are maybe less emphasis in achieving the best possible results. The results of this placement may be used as input to the tool which generates capacitance constraints used to derive subsequent placements. Here I perform placement and routing using a sophisticated tool by Cadence known as Innovus. Legality incorporates such constraints as the circuits not overlapping one another and remaining within the bounds of their placement area, being placed in valid orientations and in rows specified in the chip image, satisfying other restrictions supplied by either the user or the technology. Once the logic has stabilized, more emphasis is placed on achieving a high quality and legal placement. Some placement tools do ignore at least some aspects of legality during the optimization phase. Both clock optimization and power optimization, this overlap can simply be removed through a brute force technique, or overlap removal can be performed with some of the placement optimization. It is important to ensure that the quality of the placement is maintained, such as clock skew, timing, and wireability. For instance, the smallest clock skews is achieved by preventing the circuits in timing critical clock trees from moving during overlap removal. The basic algorithms used in our placement programs are simulating annealing and quadratic placement with iterative improvements. These are by no means new techniques, but the programs have been continually enhanced to give better results in general and to support the new specific technology-driven requirements. The simulated annealing placement program now has the capability of performing low temperature simulating annealing, LTSA. So LTSA determines the temperature at which an existing placement is in equilibrium and starts cooling from the temperature, thus effecting local improvements to a placement without disrupting the global placement characteristics. Both simulated annealing and quadratic placement accept many controls. They include pre-placement, foreplanning, specification of circuits to be placed in adjacent locations, net capacitance, and source to sink resistance constraints, and weight for the various components of the scoring function, including net length, congestion, and population balancing. The routing program receives guidance from the clock optimization program for nets in clock and other timing critical trees in the form of floor plan routes. The routing program breaks each of these multi-pin nets into a group of point-to-point subnets. Each of these subnets is then routed to match the delay selected by the clock optimization program as closely as possible to achieve the desired electrical and noise characteristics. You can specify the wire width and specifying to be used for each net. Clock nets are often given a wider width and spacing to reduce their resistance, capacitance, and noise. High clock speeds and long, narrow wires can result in a reliability problem known as electromigration. Over time, the movement of electrons can move the metal atoms and result in a break-in the wire. So we want to fine-tune the wires for some nets, such as clocks, and keep these wires fixed through multiple passes of engineering changes. At the end of routing, all new wire segments are assigned to a user-specified group. The routing program makes sure that nets routed in one iteration do not prevent the remaining nets from being completed. This allows me to have the program route just the clock nets in the first iteration. Once it has been verified that these routes meet the clock skew objectives, the wires for these nets can be fixed during the remaining iterations. A set of timing critical nets can be routed in the second iteration after analysis has verified that these nets meet the timing objectives. The remaining nets can be routed in the third iteration without changing the wires for the clock and timing critical nets. This methodology allows high clock skew and timing objectives to be met. It also allows timing problems requiring logic or placement changes to be identified quickly before running a relatively long routine iteration on the majority of the nets. In this segment, I have illustrated the place and route of an artificial intelligence arithmetic logic unit, ALU, for a design implemented in ASIC 7nm system-on-chip technology.